So now we're going to move into what is going to be an equally interesting segment around the use of digital twins in the project production system. So Roberto, can you turn on your camera and video, and I'll just turn it over to you. You need no introduction at this point, so take it away.
Thank you so much, Gary. So can you see me okay, Gary?
Yes, we can.
We can see you.
Okay, great. So this session, we're gonna be together for an hour and 10 minutes approximately. And it focuses on digital twins of project production systems. And the way we are going to approach the session is we have three parts. I just want to give the audience a bit of an idea how we're going to do this. Three parts. I'm going to take a few minutes to frame things around the idea of digital twins. I will share my screen in 1 minute for that. And then we have two applications. One that is focused on oil and gas field developments is going to be led by James Choo. So we're going to invite later James to join us back. And then it's going to be followed by McKinsey & Company, who we have a couple of guests from McKinsey who are going to share with us what they have been doing in terms of enabling digital twins of project production systems. And particularly two applications that they have actually done on civil infrastructure projects. After that, we will spend some time on Q&A, questions and answers, for both presentations combined. And to finish this session, we have a couple of additional guests that are coming from two universities, and we have Cal Poly and UC Berkeley, that a couple of students that will share their work and in terms of modeling production systems and contributing to this idea of digital twins. Okay. If we have time, obviously at the end, we will have some Q&A for Cal Poly and UC Berkeley, but we will have to check on time at that point. That being said, let me share my screen and position a bit more what we are going to discuss. And this is 100% about context on digital twins of production systems. So a bit of a story. So a couple of weeks ago, 2 or 3 weeks ago, I had a chance to had a conversation with Martin Fisher, who, by the way, is following after this session on an interesting presentation on the project of the future. And Martin and I were talking about digital twins, and out of the conversation came this question of a twin of what, right? And what we see, we once again, we were talking, having a discussion, and we were talking about the use of the concept of a digital twin for existing facilities. Existing facilities that are operating. It could be a refinery, it could be a plant, right? Where you want to have a digital representation of the plant and the digital component, the different components in a system, and somehow get obviously a connection between the real asset that is an operating asset and this digital asset, okay? And so that was one element of the discussion, right? But the focus today is not on that. Then we move from an asset that is operational to an asset that is being built, which is basically what we do in projects, right? And so, and we ended up talking about the use of 3D models, right? A lot of people these days, and I'm bringing this up because a lot of people these days in the industry are referring to the 3D models of the asset being built as a digital twin of the asset, right? And 3D models have been around for several years, right? Decades. So it's nothing new, right? I think the term is now being connected to the asset. But today, once again, we will concentrate on a very specific application of what we call here at the Institute digital twins. And it's a digital twin of the actual production system required to produce the asset. required to engineer and build the asset. On this side, on the left side, we have the actual real thing being built. And on the right side, can we have a digital representation of not only one, but multiple production systems? And the answer is yes. In order to do this, we need to have, as you can see on the right, a way of modeling, mapping and modeling, and digitally representing these production systems, right? Because the production systems are on the left, physically occurring, physically being put together. But obviously, we don't have the luxury and the complexity in construction. This could be deployments too, back to the previous discussion. It applies to both construction and deployments. We don't have, it's so complex that we don't have the means in a conventional way, but these days technology is enabling us to really get the concept of the digital twin and make it a reality, digital twin of production systems. So in essence, what we're discussing here, or what you will see, is a digital representation of one or multiple production systems, the actual production system happening for a project, I repeat, for a project, right? And a link that is actually a real-time link back to the model, and the model and the digital twin providing an analysis automatically using operation science, for instance, and determining what should the optimal behavior be of the production systems that are either, this could also, by the way, I should have said that, this could be at the beginning before we have an operating process, or it could be during the operation of a given production process, okay? So the concept is this linkage, the real-time link to the digital twin between the real asset and the digital asset. That enabled us to get access to a variety of information and data and insights about the performance, about what the performance should be versus what it is from a production perspective. This is not about from a conventional project management perspective, right? Those curves that you see on the left, these are not S-curves doing progress management, but it's about throughput. It's about understanding capacity utilization, understanding cycle times and working process, and many other factors that are typically associated with production processes. And so that is one concept. Now, we will take it to the next level, right? And this is part of the framing that I wanted to do for our audience today, is that because these days we have access to a variety of technology that enable us to capture data about the current performance and transfer it, we can now talk about a vision called intelligent production, right? Where we can have production systems that automatically optimize themselves as long as we have this connection between the virtual and the real production system, right? Using operation science, for instance, right? Now, what I wanted to do here very briefly, this is actually from the internet, there's nothing to hide. Companies like Caterpillar are already using series of technology for autonomous vehicles on mines around the world, right? And the reason why I'm bringing this up is because this is happening as we speak, number one, and the use of this technology connecting to specific resources like this track on the screen, and that monitoring the movements of the track and how much load, for instance, it might actually carry from point A to point B, all these data being transferred to a digital twin of the actual production system. This could be technology attached to pipes, could be technology attached to like the Internet of Things. And then we get closer and closer and closer, as Gary mentioned in his opening remarks, to the idea of a digital twin of project production systems. At the end, we're talking about having a model, something that we can visualize what that production system is, and once again, use technology as a means to connect it and have a virtual digital twin of the production system. Okay, so I just wanted to frame things a little bit because we are going to talk about multiple applications, including the students coming from Cal Poly and UC Berkeley, on what is being done about this. Okay, so I will stop sharing my screen at the moment, and I will invite James Choo to share video and enable audio, please. And James, I'm not going to introduce you as you have been in previous sessions, so let's keep it really simple. And James will take us through an application of what others are doing in oil and gas field development. So James, over to you.
All right, thank you, Roberto. All right, so we're going to actually talk about the role of digital twin in the onshore field development. As many of you are familiar with, onshore field development actually is the deployment, again, the word deployment of something that looks like this for your gas or oil production, okay? Now, traditionally, when we talk about the onshore field development, that we are talking about the actual drilling work or the actual the production at the once the wells are completed. And the digital twin is very much focused on the 3D modeling aspect of that work. And so you might actually have digital twins, as many actually refer to it. As Roberto already talked about and described, what we actually mean by digital twin is the actual production process that takes the wells and the pads from the planning perspective, activity, to the actual point of being put online. And this is a very, very simplified view, but regardless of who you are that's in the process of actually developing onshore unconventional well, this is pretty much the process that everybody actually goes through. Okay, again, this could be broken into 3 different steps depending on the different rigs you use. You can actually have multiple completions processes actually here, multiple hookups, and then main pipeline actually as a separate item that gets connected to the site. But generally, this is the process that all the onshore field development organizations actually go through. Okay, so we can actually say that's the model of the production system. Now, one of the benefits actually of being able to make that model is to be able to understand how we want that production system to behave, and use that information from the actual information of how the work is actually getting done to inform the model. So this actually can be a living system. So for example, if you actually know what this duration, the capacity, the resources that you're going to actually have, then based on the number of wells you're going to try to put on online that year or the next year, the future years, you can actually determine the WIP targets and stock targets and the required number of resources to actually achieve that output that you're actually looking for. That becomes something that you're actually using to control whether you're actually ahead or behind in terms of your WIP. Not in terms of time, but actually above or below in terms of your WIP and stocks. Okay. Now, this is something that we actually all talk about a lot, is there are many, many organizations and the systems out there that actually focus on visibility. And the visibility actually says how many pads and wells do we actually have in permitting? How much do we actually have permitted? How much do we actually have in built? Again, first step is to actually differentiate a pad that's rather than not actually responsible, over to construction, but whether it's actually waiting to be built or actually built and actually waiting to be drilled, or whether it's being built. So the differentiating the 3 statuses would be very critical. But even that point, once you actually see that, there really is not much actual action you can take if you don't know what the WIP targets are. Okay, so for example, let's actually say you actually have 20 permitted wells. Is that enough or is that not enough? Okay, unless you understand what the targets are for the overall behavior, optimal behavior of the system, you actually don't know what management actions you need to take. Therefore, setting this targets by using something like this is critical. as the work is getting done, you now actually have the actual durations that can go back, feed into the model. At the same time, the amount of rework that's actually being performed. Why is the rework actually important? Because in order for you to actually get the amount of wells you actually need outside to come out, if there's rework, then you need to actually have more work or more capacity dedicated to individual operations, or actually have more in web. Okay, so therefore this is critical to the behavior of the production system and the actual number of resources. Again, the mismatch between the required versus actual will tell us whether it's that target that you're trying to hit is feasible, and if it's not feasible, when you can actually expect it to be done. So this is one living system that actually needs to say, that can actually start from anywhere. So some organizations actually have started to say, we want to actually start doing this because we don't really actually have much data related to how these systems actually, how these operations actually function. Therefore, we're going to actually start collecting the data and use that to build a model and then set the target and go from here. Some organizations have said, no, we actually have a pretty good estimate of what we actually want to have come out of it, or let's actually start with the model and then let's actually control to it. Either way, regardless where you start, what you want is now a system that actually operates in conjunction. Okay, so by doing so, by doing the model, again, as we talked about, you can actually understand what your capacity utilization actually is, and is your bottleneck where it needs to be, and how much WIP do you actually need to have in the system. Okay, and by actually having the control element, you're constantly actually looking at your cycle time, what's your mean, what's your the variances, and the median. So that allows you to actually understand what parameters you want to actually put into your model. Okay, again, for each of the operations that you might be actually seeing. Okay. Now, one thing that we actually had done in the past is there was actually a very big effort in creating the model, collecting the data, and then actually feeding the model and so forth. But what we've been actually working on with our team is the ability to build in the actual modeling and optimization process into the tool that people are actually using to control the work, whether it be discrete event simulation or actually analytical modeling, that you can actually, you're able to actually see it from one perspective. So this is something that's that's actually already possible. Again, whether you're actually going to use your standard process to do this, or you're going to actually build a model to do this, it's something that's already been integrated so that you can actually have a digital twin that operates from the modeling to the control and the control to the model. Okay. With that, I'm going to hand it over back to Roberto, and I can answer any questions you might actually have after other presentations.
Excellent, James. Thank you so much. And it is important that our audience, for those of you who are not in oil and gas, also think through your own projects and how these examples might actually apply to your reality as we go through some of these discussions, right? If you're in the deployments, we can say, how can these apply to deployments, right? We have multiple things going through, and it's important to be thinking through all this. So thanks, James, for your insights. We are now going to move to the second presentation by Mackenzie. And so I will invite Choo and Stas to please share video and audio. Are you there?
Hey, Roberto.
Stas, how are you?
Good,
Hey,
thanks.
hi.
Gentlemen, thank you for joining us. And so let me provide a bit of context for your presentation very, very quickly and introduce you as well. And so Mackenzie has been obviously looking at the application of digital twins for project production systems. They bring to us a story and some application examples from a couple of civil infrastructure projects. They will take us through the details in a minute. And you will see some very interesting, I would say, impact, as well as how they did it. But before you share your screen and get going, let me introduce both of you gentlemen. So first, we have with us Shabanil Mitra. Shub is McKinsey's CapEx and sustainability practice. He's a member of that practice in Southeast Asia. He brings to bear his knowledge of the working across energy and material sector, especially across the EPC, oil and gas, rail, and power customers, clients, and has advised public sector, private and multinational companies on various aspects of the business to improve business performance, including shift to cleaner technology like hydrogen and electric vehicles. On the other side, we have Stanislaw Gaponenko, or Stas. Stas is a project manager with McKinsey & Company based in Jakarta, Indonesia. He served major engineering and construction and basic material clients in Southeast Asia, Russia, and the Middle East on operational transformations and capital portfolio optimization projects. Prior to McKinsey, Stas had extensive experience in fabrication, EPC, and offshore capital projects, spending 8 years with Chevron on LNG projects in Australia and working offshore in the North Sea. Stas earned a master's degree in mechanical engineering from University of Warwick. So once again, welcome to both of you. And on behalf of PPI, thank you for joining us today. And we will keep it simple. So it's really over to you.
Yeah, thanks a lot for that, Roberto, and thanks for this opportunity to present some of our work in this symposium. I will set some of the context, and Stas will take you through some of the details. What we will do today is share 2 examples of PPM application. And these 2 examples are in very different context, right? One of them is an example of PPM application at a package level, where we are trying to improve the productivity for piling. And the second application is at a project level, where we try to analyze the project in its totality and try to see how we can accelerate the overall project and move the completion date ahead, right? These are the 2 examples that we want to share today. And it is the first time that we had the opportunity to apply PPM at a relatively large scale at an Asian company. We were able to do this with one of the largest EPC contractors in the region. It's a diversified player, but particularly large into infrastructure, especially has a spike in the area of building and managing toll roads. But apart from that, it does have other businesses in process industry. It could be oil and gas, could be mining and smelting. So for this particular client, I think they wanted to improve site productivity, look at lean construction, but they wanted something beyond traditional lean techniques. I think they have been practicing some traditional lean techniques for quite some time now. And that's when we thought it would be a good idea to introduce project production systems. And the idea was not only to try and improve lean productivity at site, but the client also wanted to have a good understanding of their supply chain systems in terms of the construction at site, be able to measure it, be able to quantify the improvement through lean, and also develop internal benchmarks as they go along. Because the client at any one point in time would have a portfolio of approximately 150 projects running, and many of these projects are repeatable. So it was important for them to kind of go into a factory mode when it comes to lean improvement and site. They wanted to create these lessons learned and internal benchmarks. So improvement in one project could be translated to other projects also. That's where we came in, and there were a few projects, I think, for the client that was not running on time. We picked 2 of them. And Stas, if we can go to the next slide. We tried to look at it around 5 levers. So looking at the product design, looking at the process, looking at capacity, inventory, and variability. And I think particularly important over here, which I think was very interesting for the client, was the point around variability, because most of the time when the client used to do their planning as well as create their Gantt charts, an understanding of the variability was lacking, among others, right? So we tried to look at these 5 levers on 2 projects and also to understand the cost benefit analysis, right? So if we were to debottleneck a certain constraint, we had to add some resources. And if we were to add that resource, there was some cost involved. And whether that made sense in the context of project acceleration, I think that was a further insight when we tried to do the analysis. With that, I think I'll hand it over to Stas, who will actually share the 2 real-life examples that we had the opportunity to work on.
Yep. Thank you, Shub. And also from my side, thank you to the Project Production Institute for inviting us and allowing us to share these cases with the audience today. It's good to be here. I'll talk a little bit more about what the 2 applications were. So the first one on the left was for a harbor construction project. They're both civil infrastructure projects, and the scope was relatively simple. So I think for the harbor construction, we had some SBSP and CSP piling, capping beams, pile slabs, ducting system, some of the fenders and bollards on the marine side. But the project had some additional complexity in the sense that some of the work could only be done at certain times of the day because of the tidal waves and access to the areas. And when we started looking at it, was rather significantly behind schedule due to various technical challenges, in particular on the piling productivity. And for the second project on the right-hand side, this was actually on a package level. This was a road, a highway construction project, and we've looked specifically at one of the sections, the main bridge section, and try to improve the piling productivity on that. So again, rather simple civil scope, but also limitations for the road construction in terms of the times of the day when the work could be done, because this was in the residential area. So there was limitations on the noise due to piling. And despite kind of the simplicity of the scope, but due to that added complexity of the limitation on when the work could be done, we still managed to get some good results with the application of digital twins. So in the first case, we looked at about 20% schedule acceleration for a critical project milestone, which was halfway through the project and had significant liquidated damages associated with that. And for piling, we actually saw up to 300% improvement in the cycle time. And this was over and above what we would normally call the classic lean construction levers. So I'll just show you a little bit more on these 2, starting with the harbor construction. So the 2 Gantt charts here show what was the baseline situation and the 3 milestones, milestone A, B, and the ultimate project completion. And you can see that the case was trending to a 2 months delay against the first milestone, and the overall project completion was also trending to about a 1-week delay. And by modeling the production system in a digital twin, all the processed steps, all the resources, and also the variability levels, the performance that we saw on site, we actually managed to find a simulation where the milestone A, which had penalties associated with it, could be pulled within the target completion date, And also the overall project completion was accelerated about 3 weeks to end at 2 weeks ahead of schedule. And as Choo mentioned before, of course, there was some cost associated with that acceleration, but the digital twin allowed us to know what resources exactly at what time were needed. And at the end of it, the net benefit was still there. So the avoidance of those penalties was actually a lot higher than the extra cost that we needed to do that acceleration, do that sprint to deliver milestone 8. And this is just a representation of what the digital twin model looked like. So every one of these shapes or blocks represents a station, workstation, with inputs going in and the outputs coming out, whether being piling or welding or rebar installation. So you can see that even for such a simple civil scope, that model can be quite extensive. And each of the lines represents relationships like network schedule, showing the transfer of work between them. And once we've run the model, we do a number of simulations. So at times hundreds of simulations with the different levels of variability between the processes. And there's just 2 snapshots with the 2 settings of low variability and medium variability. And what it shows us is it gives us a probabilistic model to tell when the project is likely to be completed with all the parameters that we enter. And this is just another view of what Production Manager software allows us to do. Each of these green or orange bars represents the capacity for each of the resource types. And the resources here are can be equipment like crane or vibro hammer, etc., or workers, so manpower used to deliver welders, helpers, etc. And you can see that there is difference in height between the bars, which shows the different utilization of these resources. And the goal of the analysis is to balance it out as much as possible, which is never possible. But the closer we get to a more even profile, the better the utilization of resources is over time. And essentially, we do this in cycles to try and resolve the bottlenecks. And for this particular case, the bottleneck moved from the crane initially with the orange bar on the left-hand side to then go to molding equipment that was used for concreting, and then later back to the crane. So it took a couple of rounds to optimize this production system to give us the outcome that I shared in the beginning. And capacity, of course, does not stay constant over time. So there is an additional dimension of time which we model. And the graph here shows for 2 different types of resources of what it looked from the beginning of the project until the end. And what this allows us to do is also know when the highest utilization is, so where the kind of the peaks on that graph are, but also where the valleys are, where the lower utilization is, which allows us to demobilize the resources when they are not needed and save project cost. So it allows us to develop various delivery strategies based on the understanding of how resource utilization and capacity utilization changes over time. And lastly, I think kind of the summary of what the recommendation was after running the digital twin. So on the left-hand side, this is split into 2 types of resources: the equipment and all the machinery and the manpower. And on the left-hand side is the baseline case. This is what we started with, and this is what the client was planning to run the project at a more or less constant basis. And we've actually restructured the resource allocation with an increase, so that increase here to deliver the milestone A, so doing a sort of a sprint, and then ramping the resources down back to a lower level below what the baseline was for milestone B, and then it stayed more or less constant until the project completion. And that restructuring or reallocation of resources, depending on the time, depending on the milestones, produced, as I mentioned, a net benefit because of the ability to deliver milestone A and avoiding the penalties that were associated with that. And if I briefly go over the second case as well, so this is for a construction of a section of a bridge, and the model here on the left hand side actually looks a lot more simpler. This is because we haven't modeled the full project scope, we've just modeled the piling package, so it involves about probably about 24 steps to be able to do that. And we've continuously updated the model, similar to how Roberto mentioned in his framing conversation, with the actual productivity on site, with the progress rates on site, to run the model over and over again to give us a recommendation on what has to be changed for the best outcome to reduce the bottlenecks. And in this case, out of the 5 levers that Choo mentioned, we could play with 4 out of 5 because we were already in the middle of execution for this project. We could not influence the product design or the engineering design of what was being built, but we could change the process design. Despite the simplicity of the work being done, there was still some sequence that could be modified to improve the execution capacity. So that was one of the main levers, adding resources where it was needed, including manpower and machinery, and also changing the shift pattern for some of the resources. Inventory, so controlling the WIP, similar to the example that James shared, and of course the variability, both in terms of the external factors like weather, and also the internal ones, the performance of, for example, welders, and the quality of the work that they were doing. And for the different parts of the production workflow, you can see that the bottlenecks were quite different. So I think the main ones on the machinery side were on the for the cranes, and together there was about a month worth of schedule impact at play for resolving that bottleneck. But there was also similar bottlenecks on the manpower side, and the main one was on the riggers or the helpers that were installing the piles in place before they were driven into the ground, with about twice schedule impact at play here, with about 2 months. And similar output from the software production manager, where we tested different scenarios or different combinations of what could be done in terms of adding, for example, 1 hour to shift time for a particular type of resource, or adding another crane or a vibro excavator, or playing around with the batch size of the handoff between the different workstations. And this continuous optimization allows to find an optimal combination of resources, shift time, and the sequence that allowed us to accelerate this project and improve the piling productivity. And just a visual representation of what the cycle time looked like before and after the change. And the rows on the left hand side just show the steps, similar to what you saw with the different shapes on the model screenshot on the previous page, and the chart on the left is the actual productivity that we've observed in the beginning, or the baseline, with about 170 minutes cycle time for piling, and the overall productivity being about 2 piles per day installed. And we've applied the more classic or traditional lean construction levers, which were quite simple, and that already gave us an improvement to about 3 piles per day, or about 2 hours cycle time. And then with the application of digital twin, we went to the scenario on the right hand side, where we went to about 5, or on good days 6 piles per day. And just visually, you can see how a lot of the work in the beginning and also in the middle has been completely deconstrained through the addition of the second crane, which essentially takes that work off the critical path and is the main driver for increasing the productivity. And I think the last page, just to show the summary of what the impact was and the different opportunities or different levers that were applied. And as I mentioned, they essentially fall into 3 categories. One was the addition of resources, whether being cranes or manpower, but knowing exactly when and where and how many should be added so that the cost does not increase significantly. We've looked at the shift pattern and the work calendar, adding a couple of days for certain types of resources. And lastly, we've also looked at the sequence of work and the size of the batches of the handoffs between the different workstations. And the impact for different levers is shown on the right hand side. Yeah. So I think in summary, again, the main takeaway for us was that even in rather simple civil infrastructure projects, the application of a digital twin can certainly bring value, whether applied at a package level or at an overall project level. I think it also allowed us to build that library of benchmarks that Choo mentioned in the beginning, which also then became a reference point for the client going forward with similar projects in the future. Thank you very much, Roberto. I think that's what we wanted to share today. So happy to answer any questions, or if not, we can move to the next presentation. Yeah.
Stas, thank you very much. Very, very impressive, and Choo as well. Thank you guys for joining us today and showing your work and what organizations can achieve through this methodology, this technology, because it's really not just a methodology, it's a combination of a given technical approach and the technology to get to the digital twin. So very, very impressive. So we invite James Choo to be on video and audio again with us, please. And we're going to go through some questions and answers. We don't have a lot of time since we still have a couple of additional presenters. And so we're going to go through a few questions really, really quick. I think this is something that, Stas, you just mentioned in one of your closing comments. And James can also provide and show the 3 of you your input on this. Is the idea of creating a digital twin of a production system applicable only for systems with a large number of items going through, like what you show for wells? I think that probably we answered this question by the example that you presented on the hardboard, but I'll let you guys expand on this question. Any preference of who goes first?
Yeah, maybe I can answer that. I think I have a very, very simple answer to that. Look, it all depends on the complexity. I agree with that, because if you have a few inputs a few elementary steps, limited number of activities, sometimes the improvement is very intuitive, right? People might be able to do it just in their brain, or just using their common sense by visiting the ground. Where the digital twin becomes impactful is when you have a larger number of inputs, more complexity, because that's when maybe using simple common sense or just going on the ground and observing, the improvement ideas and the bottlenecks and the resources may not be immediately clear, right? So it's not so intuitively clear what the bottlenecks or the resources are. And that's where the digital tool helps us, right? To address the complexity, which the human mind cannot process that easily. So yes, I think the digital twin theoretically can be applied even in simple contexts or complex contexts, but it makes much more sense in a complex context.
Thank you, Choo. James, any perspective from your end?
Yeah, so I think there's two things to take a look at, whether there's the numerous actually outputs versus the numerous repeated operations. So you can actually have one facility that's actually going through a production, and that may involve 20, 30, 40 different pipe and pipe spools that is actually being installed. At that point, you're starting to already actually get repeated operations with conflict and capacity alignment between different operations. I think that so you don't actually need a huge number of items to actually be produced at the end in order to actually benefit from the actual operation science. Now, I think Shab actually had an interesting perspective. Is it worthwhile actually doing a production system model, spending the effort? Sometimes it, if you're actually going to cook 10 burgers, you may not actually want to spend the time to actually create a production system map for it. But if you're feeding 50 people, and which we actually have done in the past, we actually had to create a production system model to understand, how do we reduce the cycle time so people don't actually get cold burgers. So again, I think it's not just actually about the what are you actually trying to achieve using the production the digital twin. And when you actually look at individual projects, the focus actually is not about the standard products, repeated products, but it's a repeated operation that determine whether you can benefit from it or not.
Yeah, that's a great point, James. And by the way, I would like to also propose something along the lines of this discussion, that one of the difficulties in projects, I think, is that, it's not like manufacturing, right? Where you can go to a manufacturing facility and you're going to see the production system literally physically in front of you, right? You can see the production line. In projects, it's different, right? Because we have components that will be active later, and the ability to see that in a digital model of even when things have not yet physically occurred, right? And you're trying to influence, obviously, become much more proactive. I think that's what is one of the advantages that the engineering and construction industry should take from things like this, right? There's one more question, by the way, and this is unfortunately the last question for the three of you. It seems to be a question that has two parts. Let me start with the first one. The first one is about what other types, in addition to oil and gas field development, James, that you introduced, in infrastructure, what other type of production systems you think this can be applied to?
Well, I think you already actually hinted on it this morning. We're actually already doing this in the data center business, and actually on the deployment side of the business. So I think those are two right off the bat that they can actually benefit from. At the same time, this is being applied to manufacturing and let's say facilities that are in the building things actually for the construction industry as well as the mass marketing industry. So it's not something that's actually just actually for the oil and gas or the infrastructure, but any production system that actually that's actually producing something that you like to actually optimize the performance of.
Excellent. So any perspective, Stas and Choo, about you guys operate globally? across multiple markets. So any additional thoughts on this?
Yeah, so look, for me, it does not have to be oil and gas specifically. I think the concepts are pretty much applicable across different types of projects. And what James said, and what we also felt while we were applying PPM in the context of those two particular projects, is the benefit is the benefit can be multiplied or scaled when the activity is repeatable, right? So essentially, it's about looking at a few specific activities, trying to improve the cycle time. And if that gets multiplied by, say, 100 times over the course of the project, that's where the benefit comes from. So I would look at repeatable activities, could be small, but when you improve a very small activity also by 10%, but multiply it with 100 or 1,000, it really makes a big difference to the overall project.
Excellent.
point.
Thank you.
One more thing to add, Robert, if you don't mind,
Yeah, go
is
ahead.
that so you can actually look at this from a project perspective from an organization. You can also actually look at it from a shared supply chain perspective, right? So you might be actually using something on multiple projects where you actually are now competing with yourself because of the shared capacity in your supply network. So by actually having a production system model of your supply network, you can actually start to understand, how do we actually make sure that that specific production system or the value stream behaves the way we want it to behave.
Yeah, you're right. So we probably have 1 more minute. So this might be quick answers, but I want to pose the question to you guys. The question here, let me read, let me make sure I get this right. How do you think this approach, obviously referred to digital twins, complements current project management practices? Any quick answer to that?
Again, I'm not sure. Again, each organization has different current project management practices, but actually, take the traditional project management. PMI is a description of project management. I think this again that actually has its role to play, but I think PPM is something that that can be actually augmented, and that does not actually have to rip out the traditional practice until you actually identify yourself that there might be duplicate or actually better ways of handling things. So
Yeah.
Yep.
Yeah, I agree with you. I think PPM goes pretty much in line with PMI, or PPM is rather a sub-element of PMI, but I think very, very closely aligned with, say, project management practices. Yeah.
All right. So look, I really want to thank you, the three of you, on behalf of PPI for the time. I know it's really late in the middle of the night for you guys, for McKinsey. And so thank you so much. We're going to now move into, we were not able to answer a lot of the questions coming in, so apologize to the audience, conscious of time. But we will move to our next section. So thank you, Stas. Thank you, Choo and James.
Yeah.
Appreciate it. So with this being said, we'd like to invite Corey Nalder from Cal Poly and Guillermo Prado from UC Berkeley. Corey, how are you?
Good. How about you?
Excellent. Guillermo, where are you? Okay, now I can see you. So before I introduce you guys, let me position this a bit better for our audience. It is important to highlight that, one of the PPI objectives, not the only one, a very important objective is to develop and disseminate the body of knowledge of PPM. And this is a combination of doing certification programs, doing research, and also this collaboration with universities like Cal Poly, in the case of Corey, and UC Berkeley in the case of Guillermo. And so there are other initiatives that later on we're going to hear about what PPI is doing with educational institutions. But today, we have the chance to collaborate. PPI had the chance to collaborate with Corey, which we will start with you, Corey. And Corey is probably a great example of a professional. She's no longer with Cal Poly. She's working in the industry, correct? And you finish your undergraduate studies. But let me introduce you a bit more on this. So she's currently a project engineer at Clico. She's a recent graduate from California Polytechnic State University in San Luis Obispo with a Bachelor of Science in Construction Management, where she completed her senior project in the area of project production management. She has worked mainly on industrial projects with range from a 3.4 million square foot fulfillment center to a 500,000 square foot manufacturing facility. And so, Corey, you had the chance to apply and learn about project production management and start modeling production systems as part of your undergraduate studies, right? I think you are a great example of a professional that comes out of school with not only more traditional, perhaps, construction management, project management, thinking and idea, but also with a stronger focus on production. And so thank you for joining us today. And that being said, I'm going to basically over to you, and you have a few minutes to share what you did at Cal Poly. Okay. You might want to share your screen.
Thank you.
Thank you, Corey.
Okay. Thank you again to PPI for allowing me to present my research. This is exciting. It was originally just my senior project at Cal Poly, but being able to present it for quite a few people, it's an honor. So I appreciate it. And thank you for inviting me. So again, to restate, I work at Clayco as a project engineer now. I was an intern there, and that's kind of also what got me into this specific topic. But I used project production methodology to compare on-site prefabrication steel erection to traditional stick-built. So the intent was project production management provides continuity, predictability, and optimization of a process in comparison to the traditional approach of project management. We generally see project management taught in schools, so it was an honor and great experience to actually be able to be taught project production management as like another class, so I could compare the normal traditional style to this new methodology and this new delivery type that is definitely being implemented. Project production or project management is constrained just by scope, budget, and schedule. Project production management incorporates operation sciences into that traditional delivery method, which enables the additional focus on demand, production, and variability. The objective of the research was to actually explore the benefits of project production management when implemented. Project production management can be easily applied to prefabrication. Prefabrication provides that continuity, reduced variability, and easy assembly alterations. So I was interning when I was actually introduced to a new type of style of steel erection. It was being patented by Building Zone Industries. So if you can see in the little photo, there's this panelizing system, or a panelizing table is what they call it, where they place joists and metal decking on top of this table. They then create a system. I refer to it as a panelizing system. Then they lift it, pick it up, and transport it into the bay and put it in the bay, which reduces the amount of time their workers are at elevated heights and when actually implementing this system. So my research then focused on the capacity utilization. I wanted to compare the two methods, the traditional stick-built versus this new on-site prefabrication style of steel erection, again, with that emphasis on the capacity utilization. So my methodology, I wanted to begin with a main constant, which was I created a warehouse in Revit. The warehouse was comprised of 2 stories. It was 224,000 square feet, and it was made of 140 bays. The bays were about 40 by 40 feet. They had 6 joists, and then it was 32 metal decks in each bay. And then, your traditional columns as well as girders and beams. So after I had that model and I could apply it to both types of steel erection, I then interviewed BZI so I could get their production rates as well as the durations. So one of my main things I produced this Revit model to them, and they gave me a duration for about 10 days to complete this large of a warehouse. And that include all the detailing, assembly, items like that. They generally complete about 35,000 square feet per day in their steel erection. They average about, again, I'm going to refer to it as a panelized system, in about 40 to 45 of those on that panelizing table per day. And then it takes about 10 minutes to create that panel system. It takes about 3.5 to 7 minutes to transport the panel system from that panelizing table to an actual bay and then to place it. So I took that duration, those production rates, and I created in PPI's process mapper, as you can see on the screen, the on-site prefabrication and then the traditional model. And I put those production rates in both of those so it could be applied. And I ran through the system to see what would happen when these production rates were applied to both methods. And so then I could compare the capacity utilization for the crews working on it. So my results, I basically concluded that capacity utilization was reduced for the on-site prefabrication in comparison to the traditional stick-built. Some major differences that we can see is that BZI displays reduced capacity utilization in the areas of transportation, joist installation, and bay erection. Differences that I want to also point out is the differences in crews. It required to place the joists and metal decking on the panelizing table versus being raised at an elevated height. And it also requires different transportation styles. However, I could still apply those production rates similarly to each style and method. I also want to just kind of touch on the fact that reduced capacity utilization means that the crews are being utilized less to meet those demands of production. And so continued exploration. I've also reached out to BZI. They have actually referenced my research in some articles. I have that linked and I will be able to show you as well. They're continuing this idea of looking at the assembly process. And a lot of companies we're seeing are implementing project production management to actually view the operations and systems. And so they have a better idea of variability and can control that variability and provide better continuity of their product as well. So one of example is they implemented what's called a wall master, and it actually allows IMP installation system to enhance safety, efficiency, and simplicity of IMP walls. So again, similar to that panelizing table, it's performed on the ground and then lifted into place. And then just to show you a little bit of their website, kind of referencing the research. And they've also found that this provides, again, their workers are not at high areas, and they're not in the air for as long. So which again provides better safety for them overall. And then again, like I had mentioned, it reduces their capacity utilization of their crews.
Corey,
Thank you.
if you're sharing the link, we're not seeing it unless you were not.
Okay. If you want, you can also, once we share the slide deck, I believe it can follow the link. I don't believe it's shared screen, but
Okay,
I can go back if you'd like.
That's fine. Yeah, let's do it. Let's take a look quickly, just so our audience can see the impact of your work. And Guillermo will be with you in a minute.
And I believe, can you see it now?
No, for some reason it's not coming up, but
that's okay. The link will take you to it.
Yeah,
Thank you.
Excellent, Corey. So thank you so much, and also on behalf of PPI for your work and interest in production management, right? And so now we want to move to Guillermo Prado from UC Berkeley, and Guillermo, you're with us here on video. Yes.
Yes, I am.
So let's get ready with your presentation. Just conscious of time, please. And as I provide a detailed introduction for yourself. So Guillermo is actually a graduate student at UC Berkeley at the Engineering and Project Management School or program, more specifically in the Civil Engineering School. And Guillermo has worked with public and private organizations in South America and North America, in the implementation of building information modeling. Guillermo is part of a technical committee that assists the Peruvian public sector. He's from Lima, Peru, with the development of the national BIM policy. His current areas of interest include BIM, lean production, application of operational science in project delivery. He earned a civil engineering degree from Pontificia Universidad Católica del Perú, a certificate in virtual design and construction from Stanford University. And currently, as we said, he is part of the engineering and project management Master of Science program at UC Berkeley. So Guillermo, welcome to the symposium, and it's over to you. You have a few minutes for telling us what you're doing.
Thank you, Roberto, for the introduction for the Project Production Institute for including this work. I'm going to present part of the research that I am developing as my master thesis, which is called Impact of Production System Design on Project Performance and Operation Science Analysis in a case study in construction. I will show to you what were the research questions of my research. Will explain what is the production system that I mapped, modeled, analyzed, and finally, I will summarize the most important outputs and conclusion of this study. The research questions are related to how can we apply operation science analysis, including their graphs and equations, to find the impact of production system design in project performance. We are using a case study in building construction to understand how operation science lens can help us to understand better this relationship between production system design and project performance. And what are the assumptions and under what circumstances we can develop these methods. The production system that I'm going to talk about is a cladding on-site assembly of an off-site production system. We are going to talk about, since the components of the cladding system arrive to the project site, how the EIFS panels are installed on the building elevation, how the windows are assembled through the openings of these panels, and finally, how these components of the cladding systems are cogged in the building elevation. As you can see in this slide, the process that I mapped is divided in three principal chunks of work. The first one is related with the EIFS panels installation and inspection, then the windows installation and inspection, and finally, the development and inspection of the cogging. I'm focusing on understanding the demand under this production system and how it behaves under these circumstances. I use a demand of 16 EIFS panels per day to be installed. It's important to mention that these are engineered to order elements, and this map has been enabled by SPS Project Production Optimizer and Simulator. An important part of the process mapping is to understand how to collect data, in this case, data related with production parameters. Throughout the different interviews and meetings that I have with the project team of this construction process in Northern California, I collected the project plans. And by using the 5 levers of project systems optimization by PPI, I try to understand what are the assumptions that I have to make in order to provide reasonable assumptions to understand what are the transfer batch, the process batch, demands of each of the items that are flowing throughout the production system, as well as the process rates and process times of the different steps involved in this production system. These 2 tables represent the data and the input that I use for developing this production systems model. Then we have the outputs under the demand of 16 EIFS panels per day to be installed. As we can see in the first graph, the relationship between operation science metrics under Little's law are explained by throughput, working process, and cycle time. This green horizontal line represents the demand of 16 panels per day, and these other green lines in the upper part of the graph represents the maximum throughput. As we can see, since the demand is below the maximum throughput, the production system can respond positively to the current demand. We can see as well in the second graph, the capacity utilization of each of the resources. The bottleneck in this case is the last resources with a capacity utilization of 83% approximately. And we can understand these metrics better in this table below, which shows the operation science metrics, working process, throughput, utilization, and cycle time, and how that relates with project management metrics, in this case, duration. I also included the real duration of the different process included in the production system, which is this last column that validates the results of the model since those two pieces of information are similar to each other. But I then changed the demand to something larger. I enlarged the demand, and instead of 16 panels per day, I used 20 panels per day to see how the production system is behaving under these new circumstances. As we can see in the first graph, the demand now is above the maximum throughput line, which means that actually the production system as it was designed before cannot perform positively under these new circumstances. This can also be understood by the second graph, which shows a red line under 100%. And two of the resources used for these production systems are going above that, which, as we can see from, as we can understand from Kingman equation, when a resource is going closer to 100% or above that, we are going to see cycle times that are very large, which is the result that I am showing in this table below, in which the working process and cycle time are going to infinity because the utilization is larger than 100%. Between these two results, I conducted sensitivity analysis of the demand. I developed 12 runs, changing the demand of all the items of this production system to understand how the demand makes changes in operation science metrics and project management metrics. These results are shown here, part of them. One important outcome of this analysis is to see how the bottleneck, which are those orange cells, change from one run to another, which means that it's not always the same product flow that causes bottlenecks on the production system. We can understand that by seeing how the orange boxes are changing from each of the runs of the sensitivity analysis. We can see on the second graph how the different operation science metrics are changing by a different demand, which help us to understand how we can impact positively these metrics and therefore have a better project performance. Finally, the main conclusions of the study is that actually we can collect data by making reasonable assumptions from the project side to understand the production parameters that we have to include on our production systems models. The operation science analysis equations and the graphs, therefore, are applicable to any type of construction process. We conducted one case study, but we believe that this can be expanded to more production systems in construction. And any change in the demand cause different behaviors in the production system, specifically in utilization and cycle time. If we want to perform positively under these new circumstances, such as the enlargement of the demand, we will require some optimization and adjustment, probably by improving process rate and process times. These were the most important outputs. Thank you for your time. If you have any questions, please, this is my email to contact me.
Thank you so much, Guillermo, and also Corey. I think it's impressive work coming from two different universities in collaboration with PPI. A young person like Corey being from the university, now working in the industry with all these ideas about capacity utilization. Guillermo, a bit more seasoned person, professionally speaking, in terms of having worked in construction. It's also learning this at UC Berkeley and incorporating that into his personal toolkit, if that makes sense, right? And so from a PPI perspective, I just want to say that this is that the Institute is looking to achieve with universities and younger generations, right? The concept associated with operation science and the methodologies like PPM and science, are being introduced in our younger generations that are coming as engineers, as construction managers, as project managers to the industry. So excellent work to both of you, and keep up the work. And thank you so much for being with us today. We really appreciate it.
Thank you.
Thank you.
Thank you both. Before we move into the next session, I'm going to steal, let's say, a couple of, I know we have Martin Fisher already with us, but I wanted to address a couple of comments I believe we saw in in the Q&A here. The first one is a question. It's, I believe, about the presentation McKinsey did. This is great. I'm not completely clear whether the impact slides were potential impacts from the simulation or whether they were implemented and achieved. I think the short answer is the impacts were really a combination. Elements of were implemented, like they physically added more capacity in some cases and were able to remove some capacity, right? And in other cases, because you're talking about looking forward, is what the digital twin was actually proposing as the optimal approach. And so it's really a combination of both. The next question is about how long does it take on average to implement PPM, more specifically the 5 levers and the digital twin on a complex project. I can provide my opinion on this particular question, and the digital twin can be implemented, I would say, in about 4 to 6 weeks total, including an analysis done to this. It could be faster, but if you're talking about a complex project, which is the question, it depends on how many production systems we are talking about, right? But roughly, just to give you an order of magnitude, within 4 weeks, about a month or so, you could have literally a digital twin up and running with the technology that we have access today. Okay, so I just wanted to address those two questions.
Hey, Roberto, can I throw in something on that? We
Yes,
found
please.
trying to use that or experimenting with that in Chevron. What really drove the timeline was our ability to provide the data and the information that was needed to do the modeling.
Right.
It wasn't
Right.
the modeling. The modeling itself is actually surprisingly simple to do. The experts can pull it together very quickly if you have the data.
Yes, yes. And one thing that, by the way, Guillermo and Corey did as part of their studies is the data gathering process and a bit of the translation that they had to do in some cases, right? And particularly Guillermo, I want to speak for him on this one. Sort of he learned by doing, and he realized that the industry, in many cases, when you talk about capacity utilization, they don't really understand what it means. And so you cannot come forward asking, hey, can you please give me, what is the current capacity utilization rate? It's not gonna, you have to answer these type of questions in a different way, right? They might not be thinking about cycle time. So you have to ask about probably some rates, right? And the capacity, number of crews. And so there's a bit of translation sometimes that need to be done. So I think that's a great point, but it's not that complicated, right? And the value, it's much larger than potential time that needs to spend on doing some translation on one piece of data to another piece of data. So Gary, I think over to you for the next session.
Okay, very good.
Excellent. Thank you. Bye-bye.